time, let me just, oh, I'd forgotten where we left off. We talked about a very particular, unusual probability density function that has to do with, if we were talking about, remember, rho of x tells us the relative probability of a measurement of the position of a point-like particle. It's got to be real and non-negative. In other words, could go down to 0, but it can't go negative. And it tells us the relative probability in any region on the x-axis for a particle who is stuck on the x-axis. So we're just talking about particles that can only move in one dimension for simplicity. And we asked the question about something like, suppose rho of x, this probability density function, is supposed to represent a particle that's just sitting at a particular point, x0 on the x-axis. Well, the probability of finding it at any x except that spot should be 0. So it should be 0, 0, 0, and then 0 over here. And yet somehow there's got to be an area 1 under that function, right? Because the probability of finding it anywhere on the x-axis is supposed to be 1. And we said that's related to the total area under this curve. So the area under this curve, we're thinking of it as a very narrow, and of course it has to be really tall, spike. In fact, infinitely narrow. And if it's going to have area 1, it probably has to go infinitely tall too to keep that area equal to 1. Okay? And this probability density function is denoted by a symbol delta. And the argument for this particular one, a density function that's centered on x0 and it's 0 everywhere else, is written delta of x minus x0, and that's called a Dirac delta function. So we want to, because that's not, well, it's not really a function because functions have to have finite outputs everywhere, and this one is perfectly okay everywhere except at x0, and then it's got to go up to infinity. So you wouldn't really call it a function. But nonetheless, Dirac defines this, and it's a perfectly well-defined, what sometimes people call it generalized function or a distribution. It's not meant to make sense by itself, but it does make sense under integrals. So let's look at some properties of this. So we should think of this as sort of a limiting case of a probability density function that maybe is, one way to think of it is a very narrow kind of Gaussian or normal distribution centered on x0. We're going to make sure the area is 1. And then we're just going to make it thinner and thinner, make the standard deviation smaller and smaller. And of course, if we keep the area 1, it's going to have to get taller and taller in the middle. So we're just going to think of this as a very, very thin, very tall Gaussian function, if you like. And let's go over some of the properties of this function. Properties of delta of x minus x0. Okay. The first property is just the value of it. So if we wanted to write it as a multi-part function, delta of x is a function that is, this is sort of slightly simpler than this one. It's equal to 0 if x is not equal to 0. And it's infinite if x is equal to 0. So again, it's not really a function. So when you can think of delta of x, this Dirac delta function, without the x minus x0 in it, it has a spike at x equals 0. It's 0 everywhere else, and it's infinite at x equals 0. Now, we all know from our high school algebra when you talked about translating functions or transformations of functions, if you replace an x by an x minus x0, what do you do to the function, graphically speaking? You translate it. So if x0 is 5, so I replace x by x minus 5. I just take the whole shape of the function and translate it in the positive x direction by 5. And if you subtract off a negative number, then you would move it to the left and so on. So this function, the basic delta function, has its spike at x equals 0. Delta of x minus x0 then has its spike centered at x0 rather than at 0. So that just kind of defines what it is. So I mean, I could write the multi-part function for this. Delta of x minus x0 is 0 for x not equal to x0, and it's infinite if x equals x0. Okay. Second property, it's normalized. It has area 1 under it. Somehow, mysteriously, the integral from minus infinity to infinity of delta of x minus x0 dx is equal to 1. Of course, I'm integrating, and I'm thinking of this as a very narrow Gaussian function. So my range of integration has to at least go from before x0 to after x0 if I'm going to get the area 1 under the curve there. So you could also write something like the integral from a to b of delta of x minus x0 dx is 1 if x is between a and b. If x0 is between a and b, if the location of the spike is within the range of integration, and 0 in all other cases. Okay, so just think of it as a formal definition. We're saying, yeah, I know it's not a real function, but we're going to pretend it's like a really narrow Gaussian. It's still got area 1 under it, and we can make that happen. Third property, and this is the one that we really need to know, and it's great. If you ever see a delta function under an integral, almost always that integral will be completely trivial to do. You don't have to pull out all your toolkit from Calculus 2. So the third property, I'll put it over here. If you have the integral from a to b of some function sitting next to a delta function with its spike centered at x equals x0, and you're integrating, what is that equal to? Well, that's equal to f of x0. All you do is evaluate this function at the point where the spike of this is sitting at. Evaluate that function at the point where the spike is. As long as the spike is between a and b. If a is less than x0 is less than b, that means if I integrate over the spike, somehow we'll prove this in just a second. I replace the value of the function with the location where the spike was, and it's 0 in all other cases. Okay, so notice that's nice. I don't have to think about how to do this integral. I just say, hey, there's a delta function sitting next to something. That function does have to be a nice function. So we'll make the assumption that f of x is a continuous function. There are probably cases where it could be discontinuous, but the proof I'm going to give right now is for if it's continuous. So let's prove this. Proof. And of course, if the spike is not between a and b, it's really easy to show that these two sides are equal because the right-hand side would be 0, and we're integrating, and the integrand is 0 everywhere there because one of the factors of it is 0, right? We're integrating, if you've got a spike here at x equals x0 and you're integrating from here to here, it doesn't matter if I'm multiplying by another function, that function is being multiplied by 0 in that region. So I only need to do the case where a is less than x0 is less than b. The other case is pretty easy to figure out. Okay. So let's work on the left-hand side. Since I'm integrating from a to b, this integrand is going to be 0 everywhere except just around where the spike of this function is. So can't I replace the integral from a to b of f of x delta of x minus x0 dx with an integral from where the spike is minus a tiny bit? I'm just going to write that as x0 minus epsilon, where we're thinking of epsilon as a really tiny quantity, to x0 plus epsilon of the same thing, because everywhere, the only parts of the integration I'm going to throw away here are 0, since delta of x minus x0 is 0 everywhere outside of that region. So I might as well just do the integral for the part where I really have to think about it. Now, we're assuming this is a continuous function. Continuous functions, you know, they change their value. But if you're integrating over a very narrow region, right, from a value minus epsilon to a value plus epsilon, the value of any continuous function is approximately constant in that region of integration, right? So we're integrating through a range of x values that's very close to x0. So the value of f of x is very close to the value of f evaluated at x0, because its output is almost constant at f of x0. So I could replace that with the integral from x0 minus epsilon to x0 plus epsilon of f of x0 delta of x minus x0. And then what can I do to simplify this integral? Yeah, this is now a constant. It doesn't depend on x anymore. So I can pull it out of the integral, and what's left is 1, because we said the area under the curve is 1. We've integrated only over the part where all the area is, so it's still 1. Right? So I pull out that f of x0, and what it's left multiplying is the integral of the delta function over a range that includes its spike. Okay, so we'll put a little check mark next to there. We've justified that. The other case where x0 is not between a and b, it just gives 0 on both sides. Okay, we're going to end up getting a lot of mileage out of the delta function in this course. So don't think of this as just a weird mathematical aside. This kind of case for a probability density function is going to happen quite often. And it's not bad, because all the integrals you have to do using it are easy. Okay, questions on that? All right, so we've been talking about probability density functions, but back to physics, now what we need to think about is, how does our wave function, psi of x and t, if we're talking about a one-dimensional wave representation of a wave, how does that relate to the probability density function? And I think, let me share the screen here now. I think I wanted you to just to think back to what you learned in modern physics. Here's a voting question. You know, I don't have a ton of voting questions in this course, but let me hand out some voting cards. You can just bring them. If you ever forget your voting card, you can just use your fingers. I'm assuming those of you who haven't had me, Dr. Rodenborn uses something very similar. So here, you know how it goes. You just fold it to the appropriate response and vote. This is just to disentangle this. You know some relationship between psi, the wave function, and and something having to do with probability. And here are some choices for the relationship between psi and the probability. Quite a few of them, including the, disconcerting none of the above answer. Take a look at those for a minute. Think about which one agrees with what you know from modern physics. Alvis, of course, you can just use finger symbols if you want.
All right.
Okay, let's just see a vote. I know it's kind of a wordy thing that takes a while to look at, but if you've got a vote, we can argue it out afterwards. I just want to see where the class is. If you've got something you want to vote for, you can hold it up next to your head or on your chest or something like that.
All right.
Okay. Some people are still turning. It's okay if I mean, they are sort of confusingly worded. That's kind of on purpose to really make sure we get the details right. But I see a couple of D's, a couple of F's, and a couple of G's. Anybody want to make a strong argument for their answer? Yes.
Oh.
Yes. Yes, yes. So we're integrating from minus infinity to infinity in all of those cases. So it should just be 1. It shouldn't have anything to do with psi if it's normalized. So you're right. The correct answer here, I know it's, why am I not advancing here? Here we go. None of the above. Some of them sort of look tempting. Everybody, hopefully you know it has something to do with the magnitude of psi squared, right? And this is what is called the Born interpretation or statistical interpretation of psi. It means what's the relationship between if a particle is in a state psi, what is rho of x? How do we get rho of x from it? And the answer is you first calculate the magnitude of psi squared. That means psi star times psi, right? The complex conjugate times itself. Evaluate at the time that you want to know the probability density, because the probability density could be changing as time goes on, right? Those peaks that we're seeing in the probability density could be going up and down. We evaluate psi at the time we want and take psi star psi, and then what we'll get is just a function of x because we've already evaluated it at a particular time. And that had to do with some of the responses in there, but none of them involved, saying something exactly like this. So the interpretation is, how do you use the probability density? Well, you have to integrate between a range of values, and that gives you the probability of a position measurement giving a result that's in the range over which you integrated, giving a result range between A and B. What's that probability? Is it a third or a quarter? It's got to be between 0 and 1. And so now, I guess there's an important point here, and let me just see what's on the next thing. Well, actually, let's look at some of these. These are some of your reading responses before we go on and talk about the normalization of the wave function. Some of these don't have to do with this, but I'm confused on the origin of Born's statistical interpretation. Was it just noticed through experiment that psi squared was related to the probability density, or is there a theoretical derivation between this relationship? There's no theoretical derivation that I'm ever aware of. It is a new postulate in quantum mechanics. So it's sort of like, well, de Broglie said matter can be represented by waves, and the question is, what does the wave have to do with anything other than a nice picture where we have an integral number of wavelengths in the Bohr model or something like that, and constructive and destructive interference. And people realize that, in things like the double slit experiment, you had these sort of weird random statistical kind of filling out of probability density functions. And so it was postulated, and it was a matter of it was an experimental question to answer of whether or not it was psi squared that was the correct thing. But it seemed like if psi is going to be inherently complex, you got to make it real somehow. And the magnitude of psi squared could have been a possibility. Just the magnitude of psi. In other words, take how big that complex number is at every x value. Maybe that was the one. But the magnitude of psi squared is somewhat simpler. The reading explained that in the double slit experiment, when one single particle was fired at a time that the particle interacted with itself, how can a particle interact or interfere with itself? I mean, that's a good question, and that's the whole mystery of quantum mechanics, but we're thinking of representing the particle by a wave. And so the idea is waves can interact with it. When we say there's a wave, the wave is distributed throughout space. And so different parts of the wave can interact with other parts of the wave and add together or destructively interfere. So when we say it interferes with itself, we're thinking of the particle not as a localized entity, but rather as something that's spread out through space. And the relationship with the localized entity comes from the Born interpretation that's saying, yeah, we're going to calculate things with waves, but then ultimately, if you're going to detect where the particle is, the magnitude of psi squared tells you the probability density. Griffiths asserts that we dare not ask why and how a particle chooses a location when the waveform collapses. I'm sure physicists have dared to ask this question. Do you have any insights into why this phenomenon occurs? I don't think anybody knows anything. It's somewhat disappointing, but then again, it can be kind of exciting if you think, if you can make this contribution, in other words, have some more mechanical what is going on during the process of the collapse of the wave function. Nobody's really made any headway with this for over, it's been about a century now. So that's a big question mark, and nobody really knows how to think about it or experimentally probe it. It's just that the naive ways that you might think something is happening, such as, well, it's really a localized particle and it's doing something complicated and all we're getting is sort of a statistical average of it. You can show that those kinds of analyses either don't work or they make the theory more complicated if you're willing to think of it that way. That's called a hidden variable theory. So no, I don't have any good comments about that, and I don't think Griffiths does either, disappointingly enough. How quickly is the collapsing of a wave? Again, I don't think anybody knows of any dynamical description that goes from the wave being spread out to being localized. Griffiths is talking about when you make a measurement, and here we haven't really talked about this yet in the class, but when you make a measurement of position afterwards, for a very brief moment in time, the wave function becomes localized at the place where you found the electron or whatever the particle to be. But nobody knows of any dynamic process where that takes a nanosecond or some femtosecond or something like that. There's no dynamic process that anybody knows about. And you would be very famous if you came up with something that stood the test of time. Okay. We'll skip that one. Okay, and let's wait for that. Okay, let's talk about the normalization of the wave function. And this is something you've talked about a lot in modern physics, that, well, there's not really a problem with the time-dependent Schrodinger equation, but if we solve the Schrodinger equation, we already noted, and you could easily do a proof of this, just like the classical wave equation is linear, the time-dependent Schrodinger equation is linear. And that means any linear combination of solutions is also a solution. So that means if I solve the time-dependent Schrodinger equation, I'm going to abbreviate that as TDSE, the full Schrodinger equation, and I get a solution psi. I suppress the x and t. It's a function of x and t if we're thinking in one dimension. Well, let's see. I guess one thing that we can realize is if an equation is linear, 0 is always a solution to it. In other words, the function, which is just 0 everywhere, will always be a solution, because if it has any solution at all, I can always add that solution to the negative of that solution, and that would say that 0 is a solution, right? And therefore, if I start with this solution, I could say, well, let's take 1 times psi plus, I guess I don't even need to know that 0 is a solution. I could say, let's form the combination 1 times psi, let's make A some complex number. A times psi plus 0 times psi. That's a linear combination of 2 solutions. They happen to be the same solution, but there's no problem with that. So that's telling me, so the 0 part just goes away, right? That's telling me if psi is a solution, A times psi is a solution, right? So that means if I know any solution, any multiple of that, by any complex number is a solution. And therefore, there's no way for me to know which one of those is the correct one that I should be using psi stars psi. In other words, should I be using the one with a 1 in front of it or the one with a 3i in front of it? Or maybe I solved for this and this already was too big or something like that. So I've got to be able to separately normalize the wave function. So when we get a solution like this, it's always sort of preliminary. It's not directly related to the probability density function until we normalize it, okay? So let's suppose I find a solution, psi, and I calculate the integral from -infinity to infinity of psi star. Maybe I could do it at a particular time. So let's say as a function of x at a particular time t0 times psi as a function of x at a particular time t0. And let's suppose it's not 1. It's supposed to be 1 because we just said the interpretation of this is the probability density at time t0, right? This is rho of x at time t0. Okay, so this should be 1, but suppose there's no way I can be guaranteed that it's 1 because any multiple of that is also a solution. Maybe I found the wrong solution. So let's suppose it's some value a. What should I replace my psi with so that this would be normalized? Say that again. 1 over a psi. So if I say this is not normalized, let's replace it with 1 over a psi. Is that going to work? I don't think so, because I'll get a 1 over a from this one, and I'll get a 1 over a from this one. And so this would end up being a over a squared if I made that replacement, which would be 1 over a. So we've got too many a's in the denominator. In fact, what you want to do is multiply by 1 over the square root of a. Okay, and by the way, a is going to be some non-zero real number. Do I have that shown in the notes here? Somehow I thought I demonstrated that. Yeah. How do I show that psi star psi is always real and non-negative? It better be if it's going to be a probability density function. It's in the notes. I say, suppose at some x value, at some t, the output of psi is some complex number, a plus bi. So let's suppose this is the output of psi at some x and at some particular time. Then at that particular x and at that same particular time, the output of psi star has to be the exact complex conjugate of it, right? A minus bi. This would be the output of psi star. And if you just FOIL it out, right? If I just distribute this out, I get a squared first. When I do last, I get plus b squared, because I times I is -1, but I've got an extra factor of -1 there. So I get a squared plus b squared. Remember, when we're writing it like this, a and b are supposed to be real numbers. So this is a non-negative real number. And then outer and inner cancel, you can easily check in your mind, right? So that's telling me that psi star psi is always a real non-negative number. Okay. And therefore, well, I guess what I was going to say is this A will always be a real non-negative number because I'm integrating a real non-negative integrand over some finite region, or sorry, an infinite region. So it's going to be real and non-negative. And so I don't have to worry about taking square roots of negatives or square roots of i's or anything like that in the denominator. Okay. We'll do a worksheet in just a second, but any questions on normalizing the wave function? Yeah, Yichen. Say that again. You mean you're thinking of a function? So you're saying f of a plus bi is equal to a minus bi. F of 0 is definitely 0. I believe it is. I think you could demonstrate it pretty easily. I never really thought about that before, but yeah.
So taking a complex conjugate of psi is also
No, it is not necessarily going to be a solution to the Schrodinger equation. In other words, it sounds sort of like it might be, but just because I have a solution to the Schrodinger equation, linearity means if I had another one, then I could take a linear combination of them. But what linear combination of this, unless I already showed that the complex conjugate is a solution to it, how am I going to turn this into a complex conjugate? Well, I can't do that by multiplying by any complex number. That's not going to turn the function into a complex conjugate. It will change what output it has, but it won't change it to the complex conjugate. So no, if psi is a solution to the TDSE, then psi star is usually not. 0 is always a solution, so in that case it would work, but in most cases it's not going to be. Okay, Griffiths shows, now you might be worried because you might say, well, maybe at time t0 I find out that at time t0 it's a. I normalize it by saying, well, let's not talk about psi, let's talk about 1 over root a psi, and it's normalized at that time, but maybe as time goes on, the area under the curve gets bigger and bigger and bigger when I look at psi star psi at later times. Griffiths shows, and I'm not going to demonstrate it here, that does not happen. You have to use the time-dependent Schrodinger equation. So I'll just sort of summarize, and I'm not going to prove it here, but I'll just say Griffiths shows, using the time-dependent Schrodinger equation, that the time derivative of the area under the curve psi of x and t dx. So we're integrating, notice, this would be a function of x and t, but we're integrating with respect to x, so it's really just a function of t, and we're taking the time derivative of that function of t, and it's equal to 0. That means this quantity doesn't change with time. And so if you normalize it at one time, it's normalized for all time in the future. Okay, you can look up the proof in Griffiths. It wasn't a one-liner, so I decided to not put it in here. It's also true, we talked about, here we're concentrating more or less on rho of x, but we also talked about earlier the probability density function as a function of px, or maybe the total energy, or any other dynamical variable. It's also true that if you normalize the probability density for rho of x, We still don't know how to produce these given a psi, but the claim is if you normalize psi so that this has area 1 under it, this will also have area 1 under it once we learn how to find that function. And so will this, so will any other probability density function. So there's only one normalization to do. Okay, let's look at that. I'm hoping and trusting that you brought the worksheet that we only did the front of last time. So let's take that out. We are sketching those PDF functions. But here is one, and feel free to work with people adjacent to you on this problem. Here's a function, simple, multi-part function, but I tried to make the functional form simple so your integrals would be easy. Psi at time t equals 0 as a function of x is 2 plus I all times x if x is between 0 and a half, and it's 0 everywhere else. So the first thing you're supposed to do is normalize psi and then answer 3 questions about the probability distribution, probability of a position measurement finding the particle at various locations on the x-axis. Flip back to the Born interpretation there. So keep in mind, I made this function to make your life easy, even though it looks somewhat complicated. You have to sort of keep your eye on things, but the idea is don't be fooled or put off by the fact that there's a 2 plus I out in front. Just do what you're supposed to do with psi star times psi and do the appropriate integral with it, and you'll find that it comes out nicely. Once you get your normalization, I highly suggest that you check with someone near you what your normalized version of the wave function is. If you've done the normalization, this factor that we need out in front, I think, is root 24/5. Yes. Okay, let's go through it together. I'm going to explain it a slightly different way than I did before, which was the way I just said you could do it, and there's nothing wrong with that, is to take the function that was given, compute psi star psi, integrate from -infinity to infinity, see what number you get, and take 1 over the square root of that number and multiply that times psi. As you probably know, sometimes people do it in sort of a backwards way. They say, well, I really don't want this function. I want some unknown a times that function. And a times 0 is 0. So when I multiply it through, I just get an a on this part. And my goal is to figure out what a is. And what I'm going to do is calculate the integral of psi star psi with the unknown a in front of it, and from -infinity to infinity, and I'm going to demand that it's 1, and that will allow me to solve for what a is. Okay, so let's calculate the integral from -infinity to infinity, putting this unknown a in front of it. You know, I could have put the a out in front, but when I put the a on the 0, it still says 0. So we only need to really put it on that part. Let's see. Well, this function is 0 everywhere except between 0 and 1/2. So if I'm integrating from -infinity to infinity, I'm going to get a 0 everywhere else, except when I'm integrating from 0 to 1/2. So is everybody okay that I don't really need to integrate all the way from -infinity to infinity because my function is 0 almost everywhere, except in this little region here? So I'm just going to integrate over that region. And in that region, this formula gives me the value of the function. That a, we already know the a we need is going to be some real number. So when I do psi star psi, well, let's just write them out here. Psi star is going to be a star, but I know my a is going to be real because of the work we just did before. So I get a times 2 minus I times x. This is my psi star. And multiplying by psi, that's a times 2 plus I times x. dx. And now combining things together, I get an a squared. 2 minus I times 2 plus I, what does that work out to? 5, right? When you FOIL it out, the inner and outer cancel, so we get 4 plus 1 is 5. So it looks like I have a 5a squared, and that's all constant stuff, so I'm going to factor it out of the integral, times the integral from 0 to 1/2 of x squared dx, right? And that is 5a squared times x cubed over 3 evaluated between the two limits. So that's a 1/2 cubed over 3 minus 0. At the lower limit, it gives 0. So then the question is, what is this number here? It looks like I have 5a squared, and then I have 2 times 2 is 4 times 2 is 8 times 3 is 24. Okay, so that's what it ends up being when I find the integral from minus infinity to infinity of psi star psi. And now to figure out what a is, I'm going to say, I'm going to demand that this is equal to 1. And then that gives me a little equation I can solve for a, right? If this has to be equal to 1, then a squared is 24/5, and a is root 24 over 5, as I said up here. So this is I put the norm down there. You don't have to use that notation, but this is the normalized version of it, where I can just use psi star psi and treat it as a probability density. Questions on A? Okay, what about B? What's the probability of a position measurement finding the particle at x equals 1/4 meter? It's 0, just because the probability density of this, well, it looks like it's proportional to x squared, right? It's a multiple of x squared. So if I were to sketch the probability density that we're talking about, rho of x, it's only non-zero between 0 and 1/2. So here's 1/2. And it's proportional to x squared. So, it's going to look like a parabola with its vertex at the origin, right? And then it's going to go down to 0, and it should be 0 over there. So it kind of looks like that. That's what rho of x looks like. If my probability density function is spread out at all, then what's the probability of me finding it right at this location? I think it was 1/4 I asked about, right? And it's 0 because, the probability of finding it between there and there is really small. And as I make those thinner and thinner and thinner, it's going to get smaller and smaller and smaller, go to 0. So at any particular location, if my probability density function is spread out like this, the probability of any particular value being found is 0, because there's an infinite number of values that we could get as an output of this experiment. What's the probability of a position measurement finding the particle in the range 3/4 to 1? Well, I can see that it's 0 because the function is 0 out there. I should integrate 0 from 3/4 to 1, but I can do that in my head. It's 0. You got to remember, this is a multi-part function. It's 0 on most of the x-axis. So D is the only one that we really need to calculate. What's the probability of a position measurement finding the particle in the range 1/4 to 1/2? So in D, that would be, what I've got to do is integrate from x equals 1/4 to x equals 1/2 of psi star psi. And I already know A is root 24 over 5, and I've got one of that multiplied by itself. So that's going to be 24 over 5. 2 plus I times 2 minus I, we already decided was 5, right? And then I have an x squared dx. So it looks like my 5s cancel out there. 24 times, times 1/2 cubed over 3 minus 1/4 cubed over 3. So 24 divided by 3 is 8. So it looks like it's 8 times 1/2 cubed minus 1/4 cubed. And Mike, I don't have any great insight into what that number is, but you put it in your calculator, that's 0.87, oops, 0.875 is approximately what it equals. Between 1/4 and 1/2, and that kind of makes sense, right? If you look at the probability density function, we're saying there's area 1 under this curve, and we're doing the integral from there to there, right? That's way more than half of the area under there. So I'm expecting a number that's pretty close to 1 rather than something close to 1/2 or smaller. Any questions about that? Yes, Makai. For B? So for B, I said 0, and that is because for a probability density function that's spread out, right? This isn't necessarily true if it's one of those Dirac delta functions where it's all concentrated at one point, right? If I said, I've got a density function that has one of those spikes right at x equals 8, and I said, what's the probability of finding it at x equals 8? Then the answer would be 1. But in this case, the question was, what's the probability of finding it exactly at x equals 1/4? And the idea is, well, look, there's okay. One way to think about it is, I could integrate from 1/4 minus a little bit to 1/4 plus a little bit, right? And I would find out that little bit of area there. And I would say, well, that's too big because it includes some other values. So let me squeeze it down a little bit smaller, smaller integral. And I should really let the length of the integration region go to 0, right? And when it goes to 0, right, it would be something like, if you really wanted to do it formally like this, it would be, well, I'm going to integrate from 1/4 to 1/4 of this. If you really followed things through, you'd be doing upper minus lower and substituting in the same limits there, and the subtraction would give you 0. So that's one way to think of it kind of formally. Other questions on that one? Yes, Riley. Well, I'm looking at this form right here. So this isn't psi, but rather this is psi star psi. It looks like a parabola because I knew my a was going to be positive, and in fact, we figured out that a needed to be root 24/5. So a is a real number. 2 minus I times 2 plus I, some people did in their head and they said it's 5. Okay, so there's another real number. All of this stuff combined together is just a real number. So it's this is rho right here. The thing that's under the integral is rho of x. It's a real number times x, or a real number times x squared. And I know when I'm graphing a parabola, if somebody says graph y equals x squared, it starts off at 0 and it opens upwards, right? So that's just what I'm using, just that generic shape. Does that answer your question? Okay. In other cases, it might be more complicated to think about. Okay. 12:34. Since we're at a break point, and since the weather is already coming in, and since I'm driving somewhere, I think I'm going to call it quits here, and we'll talk about the expectation value of the distribution and the spread or uncertainty in the distribution starting on Wednesday. All right. Thank you for coming in when things are sort of closing down and I really better hit the road ASAP. I'll try to, hopefully by tomorrow, make sure the website is updated. The most important thing for you is we're still going to be in chapter 1 come Wednesday, so there's no new reading, right? I already had you read the latter sections of chapter 1, is that right? So have you read all the way to the end of chapter 1, I think? So there's no new reading. Just try starting that homework, the first 4 problems on chapter 2. I think I made them due Wednesday. I will certainly have office hours tomorrow, either via Zoom, if we have to stay home. We'll just see what happens with the weather, or here. If you're still unsure about which way to go, first of all, check with your classmates, but we can talk about it on Wednesday and we'll make adjustments if there's a panic then. Sort of an